Hello, everybody, and welcome to another wonderful day of physical chemistry. So today we're going to start on our conversation about electronic spectroscopy. However, and it's worth noting we've actually done electronic spectroscopy before, but it was only for atomic systems. And one of the things that we should remember from atomic spectroscopy is we had a lot of limitations about what excitations were possible based on things like angular momenta, energy levels, and so on. And it's worth noting that all those same limitations are still going to be in play for molecules. So, in order to talk about molecular spectroscopy, the first thing we're going to need to do is assign all of those same attributes um, spin, angular momentum, as well as new attributes like symmetry. So in order to do this, we're going to need a molecular term symbol. So this is going to serve much the same role that the atomic term symbol did. It's going to help us know what excitations are allowable and which excitations are forbidden. But the real key thing here is we're going to have to include the influence of symmetry. So we didn't have to worry about this for an atomic system because it turns out every atom is perfectly symmetric. So we were just fine there. And most of the rest of elements of symmetry were already embedded in things like angular momentum. So again, already taken care of for us. Not so much the case for a molecule. So, as you can imagine, especially these symmetry elements get a little bit messy for full molecular systems. So, we're going to try and focus on diatomic systems. In practice, you'll often try and assign a molecular term symbol for some small part of the molecule where we're looking at the excitations in question. This will help simplify things. But looking at a diatomic system, we're going to have a general form of our term symbol that, let's be honest, is a little bit more crowded than our atomic term symbol. So we're going to analyze this term symbol by breaking it down in parts. So upper left-hand corner, this is a nice familiar location. It's the multiplicity. So when we work through our molecular orbital diagrams, we were already worked on identifying which systems were singlet, which systems were doublet, which systems were triplet and quartet. It's that same multiplicity that's going to come into play here. However, this lambda term, well, this is going to be a little bit messier. It's going to be our total orbital angular momentum. So we replace the L for an atomic system with a lambda. Get familiar, we're going to have a lot of this happening with replacing Roman letters with Greek letters. So this is going to tell us a lot about the orbital angular momenta of electrons traveling around the bond. Now, our omega here is going to be our total angular momenta, again, about this internuclear axis or about the bond. So whereas this is essentially our L, this is our new J. So these are the three terms that we're used to from our atomic term symbol. And, and every molecule will have at least these three terms, even though we don't always show the omega term. But what's new for molecular systems is this idea of symmetry. So we're going to be focusing on two key parts of symmetry. The first is inversion symmetry. So we've already played around with this before. Gerard, symmetric to inversion, Gerard, asymmetric to inversion. We're also going to introduce a new set, which is plus and minus. So this is going to refer to a reflection about a mirror plane. So if I have a mirror plane dividing the molecule in half, is it symmetric or asymmetric to inversion? Or to reflection. So we've got a lot of elements here. Let's go ahead and try and break them down piece by piece. So we're already pretty familiar with multiplicity. So let's go ahead and work a little bit with that angular momentum. So this is going to be the measure of angular momentum of the electrons rotating about the internuclear bond. And it's this rotation about the internuclear bond that becomes a really key feature. Because if I'm looking at, say, something like a sigma orbital, well, those are going to be electrons. They're just going to be moving back and forth along the nuclear bond, and I get no rotation. So these are all going to have individual angular momenta, which we're going to give as a lowercase lambda, of 0. So if I'm looking at a sigma orbital, they're all 0. But if I've got a pi orbital, well, you know how I said those pi orbitals were a linear combination of px and py orbitals, or the pi orbitals were a combination of px and py atomic orbitals, and those px and py atomic orbitals were linear combinations of the plus and minus eigenfunctions. Well, it turns out it came back, because what we can do is deconstruct our pi orbitals as a linear combination of, well, those sig plus and minus orbitals. So here we're going to be referring to our pi orbitals not so much as x and y, but instead as our good old friend plus and minus. So we can think of our diatomic system as being surrounded by two pi orbitals, which is more or less a cylinder of electron density, one moving clockwise, the other moving counterclockwise. So now with these assignments of angular momenta for our electrons, we can then find our total lambda, or total orbital angular momenta, simply as a sum of the angular momenta for each of the individual electrons. Now, this actually has kind of a nice consequence. So if I have any filled molecular orbital energy level, I'm automatically going to have a total angular momenta for that orbital level of 0. So for example, if I have two electrons in a sigma orbital, well, both of them have lambdas of 0, so we're good. Same thing for the anti-bonding. Now for the pi bonding, this gets a little bit more fun, because two electrons are going to be moving clockwise and two are going to be moving counterclockwise. So I have a +1+1, but I also have a -1-1, and everybody cancels out. And the same thing for the anti-bonding orbitals. So if I've got a full shell, I'm doing just fine. And it's worth noting that so the only states that we're going to have that are going to exhibit any orbital angular momentum will be partially filled pi orbitals. But it turns out not even all of them will exhibit orbital angular momenta. So let's go ahead and try and break this down into parts with our good old friend O2. So for O2, all of my sigma orbitals are going to have a lambda of 0. But for my pi orbitals, one set is artificially going to be set as +1, one set as -1. The choice here is actually fairly arbitrary, and this is going to have some important consequences that we see for a minute. So let's say I've got something like O2. So O2, I'm going to have 3 electrons moving with +1 and 3 electrons moving with -1, which means that, again, despite the fact that I have a partially filled pi set, I'm still going to have no net orbital angular momenta. And it turns out this is going to be true for any ground state diatomic molecule. I'm going to have just as much electrons moving counterclockwise as clockwise, and I end up with no orbital angular momenta. So most of our interest is going to be focused on either excited state molecules, such as we can imagine moving one of my -1 electron over to +1, at which point we have a lot more fun, or something like nitric oxide. So if I've got NO, now I've removed one electron from the system, and so I'm going to have a single electron with a net angular orbital angular momentum. Now here's part of the trick. It's kind of a little artificial where it's going to be +1 or -1 angular momenta. So just kind of like we did with atomic systems, I'm not going to care so much about the directionality of the angular momenta, because that's going to be a little bit artificial. What I'm really going to care about here is the magnitude. So I'm going to take the magnitude of that angular momenta, again, as demonstrated by my uppercase lambda, and I'm going to assign each various orbital angular momenta its own symbol. So if I have something like oxygen or carbon, these with no net orbital angular momenta are going to have a sigma operator, or a sigma angular momentum. Whereas for nitric oxide, I have an angular momenta of 1, so I'm going to have this will be represented by an uppercase pi. So this is going to be a symbolic way of telling us about our orbital angular momenta. We're going to be most frequently encountering sigma, pi, and delta. A delta angular momenta you can imagine being generated by something like an excited state oxygen, where I've got two electrons both residing, two valence shell electrons both residing in the same +1 orbital. However, one of the things we're going to need to do to help clarify this system is to try and help use these orbital assignments to help to determine the spin multiplicity for each of these systems. So it's going to be whether they're going to be doublet, singlet, or triplet. So again, if I have a singlet case, this is most frequently going to generate with a sigma or delta. If I have a doublet case, unpaired electrons most frequently going to occur with a pi angular momentum. So let's go ahead, with this in our back pocket, let's go ahead and play around a little bit with some of my symmetry. And again, we're going to focus here on these partially filled orbitals as they have the most interesting results. So we're going to try and assign the overall molecule as having Gerard or un-Gerard symmetry, being symmetric or asymmetric to inversion. However, in order to do so, we're first going to have to assign each of my individual electrons as Gerard and un-Gerard. Thankfully, we've already done this by describing our orbitals. Bonding sigma orbitals are Gerard, antibonding are un-Gerard. Bonding pi, un-Gerard, antibonding Gerard. So then we're going to try and combine these symmetries through some basic rules. If I've got two electrons with Gerard, I can combine them for an overall Gerard symmetry. If I have two electrons with un-Gerard symmetry, such as my antibonding, the system is overly all symmetric because the asymmetries cancel. Now, the interesting case is if I have one electron with Gerard and one electron with un-Gerard, as this generates an overall asymmetry. Something symmetric times something asymmetric is still asymmetric. So one of the more convenient ways to think about this is it's going to be a lot like multiplication of 1 and -1. Symmetric systems, as we've seen before when playing with symmetry groups, can be represented by a 1. Un-Gerard as a -1. So two Gerard symmetries gives me Gerard. Two un-Gerard symmetries, two wrongs do sometimes make a right. But un-Gerard and Gerard, whenever combined, gives me a U. So let's try and use this to examine a real diatomic system like O2. So I've got two electrons in my bonding orbital, two in my anti-bonding orbital, two in my p sigma bonding orbital, and four in my pi bonding orbital, and two in my pi anti-bonding orbital. Whew, that's a lot. But notice that since everybody is paired up, and having this even number of electrons is going to be fairly nice because G times G is Gerard. U times U is Gerard, 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 and Gerard. So almost any time I've got two electrons, so any of these orbitals with two electrons will always be Gerard. So this should give me an overall Gerard symmetry. And as a result, most molecules that we're going to encounter, they have an even number of electrons. They're going to tend to have Gerard symmetry. Now, there is some notable exceptions for excited states, but it is worth noting that these are all higher in energy and thus unstable. But you will occasionally encounter them. So keep that in mind. And because all homonuclear molecules, both atoms have the same number of electrons, she'll always give me an even number of electrons. So any of their ground states are always going to be Gerard. And this is something nice to keep in mind. So this helps me tackle spin, orbital angular momenta, and inversion symmetry. So our next big one to tackle is going to be planar symmetry. So we're going to be focusing mostly here on our pi orbitals. So whenever I've got a sigma orbital, it's not really going to be affected by a mirror plane because our mirror plane of interest is going to be cutting through the bond. And sigma orbitals, well, they're just a cylinder, so they're always going to be symmetric to a plane of symmetry. However, when I'm examining pi orbitals, it's not quite so simple because our pi orbitals can either be symmetric if it's cutting through the pi bond, or antisymmetric if it's bisecting the two lobes. Now, again, here we can kind of artificially set one of our pi orbitals as positive and the other side as negative. Now, it's worth noting that this can be fairly artificial as these two orbitals are essentially made out of linear combinations. But no matter which way I cut it, about 50% of it's going to be pi and 50% is going to be negative. So if I've got a full subshell, like for example in my O2 binding orbital, this is always going to be symmetric. So I'll have plus, because it's plus times times minus, overall even. However, if I have a half-filled subshell, again like in O2, if I go up to the top, I've got plus times minus. So this shell will be overall anti-symmetric. So O2 is going to be anti-symmetric to planar symmetry. Now let's go ahead and take a look at NO. This one is a little bit messier. So if I ever have a partially filled orbital, which again can only be given by an orbital angular momenta greater than 0, so 1 or 2, which can only be occur when multiple electrons exist in one side, then we end up counting this really difficult part because my one electron or two can either be on the plus side or the negative side. And as a result, it's pretty much 50-50, or also known as it's a linear combination, so it's both. So I can't clearly assign planar symmetry for these systems. So this is going to be one of the notable cases where I can drop the inclusion of a symmetry element if it doesn't obey. So anytime you have a lambda that isn't sigma, you won't see any inclusion of planar symmetry in your term symbol. And now this leaves us with one last pesky symmetry element. So this one isn't always included in a term in the molecular term symbol, but it is worth noting because it's more or less what we've done before. It's our total electronic angular momenta. So specifically, we're looking at how spin and electronic angular momenta pair. So this can be given by our total angular momenta as our orbital plus our spin. So here we're going to be doing it slightly differently than for atomic systems. So sigma here is going to have multiple possible values, anywhere going from our spin eigenvalue to our negative spin eigenvalue. And this will produce slightly different results than a typical Clebsch-Gordon series, because it turns out that that this time our total electronic angular momenta can actually be positive or negative. So it's always going to be centered upon our total orbital angular momentum, but it can deviate based on the spin. So what we can do is use this to generate, what's important to note is by coupling our magnetic fields from our electronic movement with our spin movement, we can generate a series of slightly different energy levels as long as our lambda is non-zero. So essentially, as long as these electrons are moving in a magnetic field generated by the orbital angular momenta. Otherwise, if this guy is 0, we will have different omega values, but they'll all be the same energy because there's no coupling of magnetic fields. So enough of me talking about generalities. Let's try and use our MO diagrams to kind of describe this system. So for O2, let's try and build up a full set of term symbols. So we've already decided that O2, with its even number of electrons, should end up having a sigma eigenvalue. It is a triplet system. It should have a Gerard symmetry, as we have 2 electrons in our pi anti-bonding orbital and nobody else counts. Then the last thing this leaves me is my total electronic angular momentum. So with a orbital angular momentum of 0 and a spin of 1, I can have a value anywhere going from 1 to -1. However, it is worth noting that in this case, since my orbital angular momentum is 0, I generate no magnetic field, and all of these energies are the same. So it's going to be fairly common, especially for sigma values, to simply shorthand this as a triplet sigma, because the more interesting thing here is going to be Gerard, ungerard, or positive or negative based on, again, the orbital angular momentum. Now, if I'm dealing with nitric oxide, well, this case, we're going to more or less ignore all of the partially filled orbitals and focus mostly on that unfilled. I've got 1 electron, which is going to generate a net orbital angular momentum, because it will either be +1 or -1, but this gives me an overall magnitude of 1, which gives me a pi symmetry. I also have a doublet spin, and the system is going to be ungerard. Again, this is an ungerard orbital, and I have a single 1. Now, it is worth noting that we have no planar symmetry because we only have a single electron. So it's going to be +½ and a -½ simultaneously. So as a result, we're going to tend to ignore it. So this gives us a set of rather simplified symmetry elements. It is also worth noting, if you want to include it, the omega here would either be 3/2 or 1/2, as I couple my spin of 1/2 with my angular momentum of 1. But again, this is fairly similar to atomic orbitals. So this gives us a new set of term symbols we can play around with for full molecular systems. However, next time we're going to make use of these as we get to talk about that wonderful topic, selection rules. We have a whole new set of them for you. Till then, take care.